So today we are going to do more graph theory, okay? But I'll go a little fast today, okay? So we will try to do two topics today, okay? Two topics. We will sort of end one topic and kind of start another topic. Okay? So, so one of the topics that I'm looking at is I should call it balancing trees, okay? And this has a lot of applications in problems. Okay? So essentially, when this is like when we studied trees, we saw that from a tree, if you remove an edge, it becomes disconnected, right? So every edge is a cut edge. So we studied those things, and we had like characterizations. If it has only two cut edges, then it's a path. Sorry, two. Yeah, we did only two no cut edges, then it's a path and things like that. But today we will be looking at what happens when you remove a vertex. Okay, so basically this will be about removing vertices from trees, and this has many applications in problems. More theory can be built, but also in exam type, Olympiad type, and this kind of problems. Okay, removing vertices from trees. Yeah, so I will only do the theory of this today, and the problems I'll just give you guys maybe after the class, and you can just try, and then next time we're going to discuss it. And the next topic which I want to now go, I want to leave connectivity. We have done sufficient stuff here, and I want to go into matchings. Okay, we will see similarities, differences. This theory has more difficult and algorithms. Like here in trees, there was really only one algorithm that we did, was a minimum spanning tree algorithm to find the minimum weight spanning tree, and then we saw its application, right? But the algorithm was not so difficult. Yeah, so that's the plan. Okay, so first let's get started with the first topic. Okay, and here we will see all the partial order things, and all will be very helpful in the matchings. So let us start with the topic one. Okay. Yeah, balancing of trees. So here the key question is the key question is what happens when you remove a vertex from a tree? Okay, what happens? Let me write that clearly. When a vertex is removed from a tree. This question is like earlier we asked what happens when you remove an edge from a tree. Can anybody, before we go to the vertices, can anybody kind of summarize or say what happens when an edge is removed from a tree? This is something that we have done in some sense. So let's say about that quickly, and then
we get connected component.
okay, what happens when you remove an edge? Only one edge. Yeah,
Gets disconnected.
that is certainly true. The graph gets disconnected. Yeah, a disconnected graph. But can we say something more specific? I mean, this is already pretty specific in the sense that no matter what edge, so you are saying no matter what edge you remove, the graph gets disconnected. And all of us know this, right? Because it's a tree. Okay. And we can also say that exactly two connected components. I mean, which is kind of obvious. You can't get three connected components, right? If you remove one edge, is it possible? No, right? You get exactly two connected components. So the answer is very simple, right? If you remove an edge, you get two connected components. And this you can prove in several ways. If you want, you can go back and again try to write this. It's good practice to write, because if you have to explain this, you can't say the way I'm saying. You have to say it properly, because we have already said this earlier. So this is simple. This everybody knows. But now what happens when you remove a vertex? So let's take you guys' opinions on this, maybe some pictures and something, and then we'll try to prove some theorems regarding this. So you could have a tree. Obviously, there are some vertices whose removal does not do anything much, doesn't disconnect, and those are the leaves, the no-cut vertices, which we have explored. But in general, what can be said? Can anything be said? Vertices get non-connected from the graph. So certainly, I mean, if you remove, for example, this vertex, and obviously that vertex is gone, and the edges that are adjacent to it are also gone. Hmm?
Yeah, I was going to say that if you
Okay. Yeah, that's certainly true. Okay. Rhythm, you were saying? Okay, right. Yeah, Rhythm, you were saying something?
yeah, I was saying that if a vertex removes whatever, it's not
That's certainly, so that's like in the definition, when you remove a vertex, then its edges are removed. But can we say anything more? Is there anything that can be said? That is certainly true. If you remove a vertex which is not a leaf, then it will disconnect the graph. That's true. That's quite that's something that we know. It's a good statement, though. Yeah. So let me write that. I think this is the first little non-trivial statement, slightly. So if vertex is not a leaf, then, and it's if and only if, but just see it simply like this, then graph gets disconnected, right? Then no, I won't say, yeah, just say graph, then result is disconnected. Can we see about no, yeah, that's where that was my next question. How many connected components are we going to get? It will be exactly. Yes, exactly. So you could get more than two connected components, and that is the difference. Yeah. So uh, we can get at least two if it's not a leaf. Yeah. So yeah. So can get more than. So this is just to get intuition for these simple things. Okay. In the beginning, just get more than two components, so that you get more clear about what it really means to be doing this. Right. For example, if you remove this, which I've circled, then all these are gone, and then you get three components, kind of, right? These vertices are not gone; they are there, but they're just isolated, right? Right. So, so we see that the question is not very good. The question that I'm asking is not very precise, right? Because the answer is like you can get many connected components, right? So it can't really say much. So the next thing, since we do not really know how many components you can get, since that can vary, the next question to ask is, what's the next question to ask? So, okay, let me just write this for you people, and so that you can ask the question, okay? Since not much can be said, not much, you can think of what should be the next good question to ask. Not much can be said about number of components, or can be, What's the next question to ask? Difference in the number, can you make it more precise? Difference because there are, we don't know if there are two things here, there can be many things.
I thought was like the total number of edges in the graph minus the total number of edges in the graph by the D.
That is very simple. That will just be the degree of the vertex that you're removing.
Yes, sir, that's what I.
Right.
So the next question, in my opinion, would be like different cases, like the kind of vertices that we take into consideration and we see, like if we remove a leaf and a non-leaf, and like depending on the degree, the question differs.
Degree, yeah, maybe degree is the right thing to investigate, right? Because see, here we said if a vertex is not is a leaf, if a vertex is a leaf, means when the degree is 1, then we don't get a disconnected graph, right? So if v is a,
Degree that connected graph is at least
yes, n connected components. Yeah, that's also a simple observation, right? Because if we, and not because, but we already know this, if v is a leaf, then it doesn't get disconnected, it remains one component, right? So, and this again is very simple. Yeah, if v has degree d, then we get exactly d trees, d components. This is also not difficult at all. You can see this. You can prove it by induction, certainly, right? And you don't need to prove it by induction, but it would be good exercise to write this rigorously, either by induction or not. So maybe you should try to write this. Everybody should try to write this, though it looks very obvious. But then if to prove it, how would you do it? So maybe just note it down to the small exercises that you should do. So well, this is also fine. So we are able to say when we get d components. But what else? What should be the next thing to ask? Question. So really, when the topic is, so maybe now I should say something more precise, because if the topic is balancing of trees, okay, so the goal, let me mention, say some sort of a goal here. So the goal here basically is to, so it's like if you have to sacrifice one vertex, okay, and still if you have to sacrifice a vertex and but if you have to sacrifice a vertex and still keep the graph as balanced as possible, right? Then what vertex should you sacrifice? And how balanced can you still keep the graph? Yes, I'll define it more. Yes, what was the question, Raj? Yes. Balance means basically the pieces that you're getting, right? That's what I was going to define. The pieces that you get, we want their sizes to be as same as possible, right? The D components, we want the size of those D components to be equal. Well, they cannot be equal all the time, but as equal as they possibly can. Okay. So the goal is, maybe now I should write it clearly. The goal is to, uh, the goal is to um, try to make the D components. So there are D trees you get, right? Different trees. This breaks up, right? D components as equal as balanced. This is the balancing, okay? As equal as possible. So we want to choose a vertex V so that the result will be as balanced as possible. Okay, now I'm not asking for an algorithm. Okay, find a vertex V so that the removing graph is that. Maybe there's a very difficult algorithm for it. I do not know actually. Okay, but we are going to prove a simple theoretical result. But is the goal somewhat more clear? Somewhat clear what we are trying to do? we'll basically try to say that mathematically, what is the best thing that we can say? Okay, with regard to balancing this. Means in general, what can we say? How balanced can it be in general?
Can we try a few examples to get the sense of it? Just
Yes, yes.
balance the idea is
Yeah, right. Right. Yeah, we should do an example. So that because of the before I introduce our next parameter, uh, we'll have to, because next will come a really different kind of parameter which we may not have seen. So let's see an example. So here is right. So let us see. Yeah, if you remove this vertex, then what is the resulting tree that we get, right? Yeah, so is this good for our goal? Yeah, right, exactly. So we don't want to remove such vertices. We don't want to do this, okay? Because this is highly unbalanced. This is highly unbalanced. And so as a contrast, let's just keep it here. And that's right. Certainly not. Exactly. We are not interested about leaves, right? Because they will, yeah. V1 is removed. So now can you suggest what vertex is good to remove? Root, kind of, exactly right. I should have labeled, so V naught. Right, when you remove V naught, then you see you get a you don't get a perfectly balanced tree, which kind of tells you that you cannot hope for one in general, but you get. So maybe it would be a good idea to think how can algorithmically one, I don't know, I've not thought about that question actually at all. Uh, yeah, actually, what you said, yes, I think I am being very foolish. Yeah, because if you go to each of them, it's not so bad to go to each of them, right? Because there are only n vertices, and then you can actually decide, right? If you go to each of them, you can decide the size and so on. So yeah, and the point is that if the input is, let's say, size 100, then the computer can do it in like 100 square steps, something like that, right? Because when it goes to each and then it just counts it. Yeah, but we're not interested in that right now, because we're interested in a kind of a mathematical bound, and those things will be useful in other problems which we'll see. So these two, right? So this is balanced, right? We not removed. Okay, so this is balanced and this is unbalanced. So this is a very simple example. Okay. Uh-huh. No, actually, I cannot. That here the first level is drawn in a way that it works, but in general, you cannot say. Right. Uh, the first level can be a leaf itself. Why not? I mean, we usually draw it in a way that it is not, but in general, yeah.
just a question here. Like
Huh?
he's following up to his like suggestion. Like,
Huh?
are we representing the graph here in a particular way? Like in usually like if you have to represent in a program, you write it like you have a something that is it's the graph. Here we are not
No, here that is not important. No, here it is not.
can take any format. We have to
Yes, because we are going to derive some like mathematical bounds. So the exact thing is not important. Yeah. Represent.
define like how we are representing.
No, no. No, because it is not important. Yeah, yeah. I mean, set theoretically one can define, but that is not even useful for us. So yeah, we yes. I mean, basically, we don't have to start anywhere in the sense that we'll not do an algorithm. So yes, yeah, but we will soon see representations like matrix representation, which will be useful to count number of walks and so on. Uh, but yeah, not now. Okay, so then we kind of understand this. So then here is the parameter. Okay, um, for a vertex, I'll introduce a parameter, and the value of that parameter will reflect upon the how balanced the resulting thing is. Okay, for a vertex V, okay, if the resulting components are V1, YV1, T1, right? Are T1. So these are trees. Okay. Initially we had the tree T, and then we have the resulting trees are T1, T2, T3 till TD. What am I roughly saying? V is the vertex, and it kind of has D edges. Now again, this is just representation, rough, just a diagram which will help me to say what I'm trying to say. And this will be our T1, T2, T3, and so on, TD. Okay. So for a vertex V, if the resulting components, which will be trees, we know are T1, T2 to TD, then define, let me define it first, then I'll say the motivation, and maybe I'll ask to how it reflects balancedness. Define, um, let me just use the notation F FV to be the max, okay, the max of the size of these TIs, I from 1 to T, 1 to D. Okay, so first thing, someone please explain what this notation means, and then the motivation later.
So T can be thought of like Ti is a number, and we can do from T1 to Td and so on. It's not like Fv is just a
Yes, yeah. T1 is not a number. T1 is a tree, but yeah, but this is understood to be the number of vertices, right? Yeah, yeah. Size is enough to be said, because if you say size, then you can either say vertices or edges, because it's just one less than that, right? Max will not change. Yeah. So exactly, and it's a constant that just is universal for a tree. It's one less than, yeah. So, but I'll still just write it for formalism. Ti, the smart Ti here, I mean number of vertices. Yeah, it could mean number of edges also, but it doesn't really matter. The maximum will not. The maximum will get shifted by one, but it doesn't really change anything. So what we are saying is the size of the largest component. Is that right? FV is just the size of the largest component that is gotten when V is removed from the graph, right? That is what it is, and I'm just writing that in mathematical terms, right? So this is just size of the largest component. Does everybody agree with this? That's basically what it is, right? Okay. So if that is okay, if not, please ask. If that is okay, then why am I interested in FP, and what does FP have to do with balancedness?
so this should tend to like, right?
Yes, if it is closer to n minus 1 by d, then it is better, right? Yeah, that kind of makes sense, right? So this quantity is, but we cannot expect that all the time, right? It's the max, no, but the minimum one can be very less. But yeah, in some sense, right? It can be minimum. You don't know about the minimum, right? The minimum can be very less. The size of the smallest tree can be very less, right? You don't know, right? But no, but the smallest can be very less, right? The largest can make up for it. I mean, you understand, right? The second smallest and others can make up, and the smallest can be very less. You can't control that because a tree is such a general thing. Right? There's no other structure. It's not, even if it's a binary tree or something, then there would be some constraint. But here it is completely generally. You can't control anything. So basically, the point is then that we want to put bounds on FV, right? I mean, it would be good for us is if FV is not too big. That is generally all of us agree, right? I mean, look, if FV is big, then your graph is, hodgepodge. It's unbalanced, right? If like this tree is very big and the others are small, then it's not good. Minus n. Oh. But how does minus come in? Okay, that way. Yeah, no, that's right. Okay, right. But I'm not writing that because we are not kind of going for that because we can't achieve it. So because in a tree you can't, there will be no vertex which will make it balanced. You can make such trees. Okay, in general there will be no vertex like that for a general tree. Obviously for special classes of trees it's possible, but in general you cannot. But what we can try to do still, okay, which is a weaker thing to do, is we want to put bounds on FV. Okay, yeah, we want to put bounds on FV. So for that, let's introduce another parameter. Okay, and this is a graph theoretic term. Let delta t is, we know this, right? The largest degree. Okay, delta t is the largest degree. So then we want to show the following. You want to show that, okay, first let's show the easier one. FV is bigger than, oh, hold on. Let me just have a look. It doesn't really matter, right? Doesn't really matter, sorry. So let me just, but 1 minute, yeah, 1 minute. So I'll just call this number of edges. It doesn't matter, but otherwise the conventions can go haywire. So this is called as number of edges in TI. Okay, it's just one less, yeah. But FB, but it still doesn't matter, right? So let's just, sorry. No, we'll come to that side, but let's first do this easier one. Yeah, so if delta is the largest degree, largest possible degree in the graph, then we want to show that FV is at least n minus, and these are useful results. Okay? I mean, I missed one of these results in one of my tests in some approximation algorithm thing, but anyways, it's very simple to prove though. Let's think about it. Cannot be n. Yeah, why? Okay, so that's a proof you're saying. Okay. So try to maybe just say it in a more clear way. Just think about it. Let's others also just think for a minute. Um, yeah, I kind of understood, but let's try to say it in a more clear way.
Like I did not get why we are bringing the inequality here and with what we're trying to achieve. Because then,
Right. So we are saying that, see, we are saying that we are trying to understand this function. Okay. We are trying to understand this function. We are trying to say that if you remove a vertex, then what can be said about the size of the maximum of the biggest component? Right. That's what we are trying to say. N is a number of vertices. Right. So, right, you understand, right? Because if you, so N is a number of vertices, N is equal to number of vertices one. So let me just give the motivation for this once again. So if you can understand this function, which gives you the size of the largest component, right? Then you would know that in general, you are able to say that the size of the largest component will be at least this. And then size of the smallest of the largest component will be at most this. Right. Then you kind of have a bound, right? So then you can, then from there you can use it, right? That if it's a large enough graph, then there will be a vertex which I can remove, and you can say things, right, about the largest size, right? So that will be how it will be useful. Okay.
okay,
Okay. Yeah. I mean, it's an important function to understand. So let's first just prove the lower bound. Okay. Let's. Do we have to do it by contradiction, or is there a simple? Okay. So okay. So you're saying that if FB is bigger than this. Okay, then mhm. Chains. What is chain? Okay, no, this is the degree. This is the degree of D. Okay. Okay. So that can be used to give a technical proof, but let's just say it in a simple way. Can we say it in a simple way? Right. I mean, see, when you're removing the vertex V, then you have n minus one vertices remaining, right? Yeah. So removal of V implies n minus one vertices remaining. Is that right? Yeah. So if there are n minus one vertices remaining, and how many trees are we going to get? How many components are we going to get? And at most, delta trees. Is that right? Does everybody agree with this? Right? If you're removing a vertex V, then how many trees do you get? How many components do you get? We have already said that, right? D components, D trees, which will be at most delta, because delta is the largest. Is that right? Yeah. Or let me just write here D trees and D trees. Okay. Where D is the degree of V. Okay, so if there are D trees and n minus 1 vertices, then the largest tree should have more than n minus 1 by D tree vertices, right? N minus 1 by D vertices. Because there are D things in which it is distributed. That's very obvious. There are D things in which these n minus 1 things are distributed, right? So at least one of them should get more than n minus 1 by D elements. Right, because n minus 1 by D is the average. So one has to be at least that or more than that, right? So that implies at least one tree or the largest tree, right? I'll just say at least one first. At least one tree has more than or equal to n minus 1 by D vertices, right? Which is obviously bigger than n minus 1 by delta. So that's basically what I'm saying here. So is this fine with everyone? Right. So this is something very nice, right? That even in the worst case, we are able to say that the size of the maximum tree will be at least this. For any vertex.
And n is here the number of vertices like in the whole graph, right? In the bigger graph.
Yes, exactly. Right. N is the number, always the number of vertices that we start with. No, that is not possible. Delta cannot be 1. Every vertex cannot have degree 1. Oh yeah, that's right. That in that case, it will maximize if other components have size 1. Yeah, all that is fine. But those are special cases. But this is something that we are able to say in general, right? By a very neat application of the averaging principle, right? If the average of certain things is an average, then at least one of them will be more than the average, right? Just that very simple idea. Just going here. Okay. So that's a simple part. Okay. This can be used to say a lot of things. Okay, let me not say that you will try it in the problems. Yeah, where you'll meet with special kinds of graphs where delta will be maybe 4 or 3, then you'll be able to say, okay, that yeah, a lot of things. Now this is the slightly more interesting part. We want to put an upper bound on delta on FV, right? We want to put an upper bound on FV because that is important to us. So let's write it in a different place. Let me just make this a little smaller. Now this goes back to the earlier thing of finding a vertex for which the tree is balanced. So we want to find a vertex for which FV is not so big, right? So there is a vertex. So this is not for every vertex, okay? There is a vertex for which FV is less than, should it be, yeah, delta minus 1 times this. So there is some vertex. There is a vertex. There is a V. There is a maybe V naught. Some vertex for which FV naught, for which the size of the largest component is upper bounded by this. Let's think about this. These are the foundations that we'll use to solve some you see some very intractable questions can be solved using this, which otherwise become very difficult. So for example, if delta is 3, right? For example, if you're in a complete binary tree, right, then delta will be 3. Or if you're in a binary tree, then the delta cannot be more than 3, obviously, right? One parent and 2 children at most. So in that case, we can say that there is some vertex which you can remove, such that you will get such that the size of the largest piece cannot be more than 2/3. This is good, right? There is some vertex whose removal will guarantee you. Then without even finding that vertex, you are able to say just mathematically. You think just you don't even have to look at the graph. You need to just know that delta is largest degree is 3. Then you can say this. That's a fantastic thing, right? Is saying what? This one, which which conclusion? This theorem, this I have not proved. This is no, this is not easy. This is not, it's not trivial. This has to be proved. We will prove this, but I'm just giving a small consequence. Okay. And yeah,
Like, could you tell me the equation behind like putting this delta minus 1 by delta? Why did it like think that what
yes, so I did not think. I don't know. Yeah, I didn't think of this. But it will come in the proof when we prove it. Yeah, this is something that I have not actually thought about too much. Right, this is a good question. So I don't know actually. So it actually should come. It will come while we prove it. Something like this.
if you put this onto I had a problem with understanding like if delta is equal to 3,
Yes,
then
yes,
the come like
yes, 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 yes. Right, right. Yes, right. So when delta is 3, so and delta is 3 is what I mean is, this is not a strange. Delta is 3 comes up all the time, right? Whenever you are looking at binary trees. Okay, then you have delta. Right? This in this case delta is 3, right? It cannot be more. So if delta is 3, then you can say that in any binary tree there will be some vertex which
just interrupting. Isn't delta the degree?
largest degree, right?
Oh yeah, sorry.
Right, right. Yeah. So then this becomes 2 by 3 times n minus 1. Then it means that there is some vertex, and this theorem is not telling you what that vertex is. Okay, this theorem is not telling you what that vertex is, but it's just saying that there will be some vertex. Okay, and that's why it's that's why we have to kind of do a proof by contradiction. Okay, so there will be some vertex whose removal, which there will be some vertex which when you remove that vertex, then even the largest chunk cannot be more than 2/3 of the graph. This is the largest chunk. Sorry, yeah, right? I mean, this is the largest chunk. F V0 is the largest chunk, size of the largest chunk you get after removing V0. That cannot be more than 2/3 of the graph, which obviously means that every chunk is less than that. So the graph is not too unbalanced. There is a kind of a ratio. You have a balance, right? You have a kind of a ratio bound. It cannot be more than 2/3. So the other guys get at least 1/3. They may not, but if you choose the vertex wisely, then they will.
By this, what we can say is okay, there would be one component like which would be at least like that
2/3.
cannot be more than 2/3 of the graph.
No, not one component. The largest component.
Yeah, yeah, the largest component have ensured that. But what about the remaining? Because
Yes. No, so that's right. That's a good question. See the
they
remain.
may not divide like
Nah, they may not that, and actually we cannot expect anything better, right? Because it's just a tree, right? But if you think more closely, you can apply this result iteratively on those smaller things and maybe say something. Okay, but I have not thought about that. So that goes into a lot of Yeah, lot of things come in. Actually I don't know, a lot of things come in. So basically this is usually, it's a very delicate result, because usually it will be used as in a way of removing edges, not vertices. It will be used, see, in the exercises somehow they will use it in removal of edges. Okay, so yeah, right, okay, let's keep going. Yeah. And this number, I don't know, this doesn't have I have a meaning to me yet, this delta minus delta, but it should be, but I'm not, I don't know it very well. But basically the property of this number is that as long as some vertex, so I mean, it's kind of like if there is some vertex for which the fv naught is bigger than this, then one of its neighbors will have a lesser fv naught, kind of fv, and then it reduces till fv is bigger than this. So that's the way we'll try to prove it, but let's see. Let's first lay out the first step one of the proof. It's not very trivial. So this should be okay by now, the different components. It's a very delicate result, and lot of things are done on this. And this is, yeah, this is something which is not there in Douglas West. Okay, as far as I know, it's not there in Douglas West. So I will say more later. Okay, how do we prove it? Okay, how to show this? Let's write full such a v naught exists. Now remember, we are not claiming that I'll find a v naught. I'll just say that I'll show that exists a v naught. That's kind of looks like the only way, at least the way, if I say exists, right? Because then exists, yeah, you can't really find it, so you have to do by contradiction. Okay, so I'll just write what you said. Assume that for all v, let's do it like this. Okay, for all v, let's try to do it like this. For all v, fv is at least delta minus 1 by delta times n minus 1. Just to draw a picture. So it could have components, and this is the largest component, and this has size more than so can I make this 1 minute? I think I can write a +1 would be more stronger, otherwise I'm not using the full thing of the contradiction, right? It's the same thing. Okay, yeah. So if that is not true, then for every vertex it happens that the largest component is bigger than delta minus 1 by delta times n minus 1. Note that this result is not very useful, and you guys should note this maybe. This result is not very useful when delta becomes big, because when delta becomes big, then this kind of goes to 1. Okay, so this result is not useful there. So it's useful for special kinds of graphs like tessellations or tilings where every vertex is degree 4 or degree, those kind of things, grades, and yeah. So this is just if you assume that this is not true, so what we have to show that there is some vertex for which fv naught is less than this. Now, if that is not, Yes, right. Just to make it equal, right? So if that is not true, then it means that for every vertex, no matter what vertex I take, I fail. Meaning that no matter what vertex I take, the largest component is bigger than this, bigger than equal to this. Now I put a +1. So then what can we do? So to put more force in our method, right? Assume that FV is minimum for V. So assume that the V that we have chosen here is the one for which FV actually is the smallest possible. And yet it is failing because by our assumption. Is it okay? Now it is not necessary to do this for the proof, but I think it will just simplify it. So assume that there is a V for which, assume that there is this V for which FV is the smallest possible, but yet it is bigger than this, right? If it was less, then we are done, right? So then obviously the contradiction would come in like, I will produce another V1 or something for which is lesser than FV, lesser than this FV. So where should that vertex come from? So remember, these are the neighbors, let's say, and we have V1, V2, V3. Let's say there are only three. That's not a problem. Generalize it.
I lost the question a bit. Could you tell me again?
Yes. So basically, see, we are trying to show that there is a V naught. We are trying to show that there is a V naught for which FV naught is small. I mean, small meaning that FV naught, not small, I shouldn't say small. FV naught is less than equal to this. Yeah. And then we are saying, okay, let's assume that it is not true. Then for all V, it is bigger than this. Then even for the V for which FV kind of minimizes, even for the best V, it is still bigger than this. FV is still bigger than this. Okay, yeah. Or you don't even need to, we can just, if you just keep it till here also, I think it would work from here. Yeah, let's just investigate. So there is a V for which FV is bigger than this. Then what can you say about this V3? Because that holds the key. What could you say about V3? So for FV, this tree here, it has this size. What could you say about V3? What could you say about FV3?
That it must be bigger than the what assumption that we are like assume for all V if V is bigger. So it V3 must be bigger than
No, think that's not necessarily true. Yeah.
I was thinking taking the total number of neighbors of V3 and n into n minus
Everybody's neighbors. Why?
so that the inequality
No, but that seems very general. Okay, that seems very general. I don't know how that will work. Mm-hmm, mm-hmm.
So like we can tell that f of b is bigger than n minus 1 minus 1 by delta.
N minus 1 minus n minus 1 by delta plus 1 plus 1. Okay.
Then say that f of b plus n minus 1 into delta
F of v plus
1 by delta
by delta. Okay, okay. Sorry, this one. Yeah. Okay. By n minus 1 by delta.
that will be bigger than 1.
Right.
We assume that f of b is equal to some t.
F of v is some t prime. Yeah. This is the size of this tree. Yeah, t prime.
Yes, n minus 1 by t. So this thing we can say that this is greater than some t prime plus t double prime.
No, you may not have a tree which has this size. We wish there was, but it's not true. Right?
Maybe more than
Okay, so you're saying that there will be a tree whose size is more than this. That's obviously we have proved, right? Uh, no. But that will not give a contradiction. Right. You get the point, right? Because I mean, if there is a t double prime and the size of t double prime is more than this, then how do we get a contradiction? Let's see. Yeah. Then we get this. Okay. So we can, yeah.
cannot remove the t.
Okay. Okay, right. So this T prime is the tree which has this FV many vertices. Right. Okay. And then there must be another tree T double prime whose size is at least this. No, but the problem is that it may be the same tree. But then that is also something that you can work out. Right. If it's the same tree, then you can work that out. But if you assume it's a different tree, then these two trees are going to be disjoint. Oh, is it so easy? But it seems correct, right? But then there is a then what have we assumed about V here? That is a problem. No. But in the proof, did you assume anything about V? No, right? So then that should not work. Because obviously there will be some V for which this is true, but then what you are proving is that it is true for every V. Right. So what you have proved is that this is true for all V. Do you see the point? Right, because you have proved that for any V, this cannot hold. But that seems wrong. Right? That is obviously wrong because you can take a tree. Or you can take a leaf, and you can take a leaf, you can take some. But then I'm not able to even see the mistake. So that's even worse from my side in the sense. Yeah. But something is wrong. Otherwise, because it's not true for all. Yeah, it cannot be true for all vertices, obviously. But I can't find a mistake. Okay. Right. Maybe I have to look more closely. Anyways, this is certainly a good manipulation there. Anyway, it can, yeah. Yeah, but see, the idea here is that, look, this V3 holds the key. So what is f of V3? I mean, what should be f of V3? What can we say? Sorry, can you say again? Is fv in fv is t prime. Wait, so let me write, yeah, t prime, yeah. Summation of ti. Okay, so t1 plus t2 plus. So you're saying the rest of the trees, right? The size of the rest of the trees. Okay, right. So the sum of the sizes of the rest of the trees, how many trees are we going to get? We don't know. Yeah, the rest of the trees minus this tree. So means this is the rest of the trees. Yeah, what can you say? Hmm? Greater than or less than? Right. Less than, right? Because so you're saying that if you, so can you say the argument? Its highest component has to be, why? No, I don't yeah, yeah. So if v3 is removed, then what happens? So the size of the rest of the graph is what? The size of the rest of the graph is n minus 1 minus this quantity, right? Because that is being used by this. So the size of the rest of the graph is this. And this is where it expression simplifies, which is equal to, this is simple, right? This is just n minus 1 by delta minus 1, right? This is that's the rest of the graph, right? The rest of the graph. If v3 is removed, so if v3 is removed, that is the size of the rest of the graph. Mm-hmm. Mm-hmm. Anyone? See that if the rest of the graph has, wait, no, what was I saying? One, let's think. So if you remove v3, then very simple that this chunk, this will be one chunk, right? When you remove v3, so when you remove the yellow, when you do this yellow cross, when you remove v3, then this is the rest of the chunk, right? And hmm, why? Yeah, this one is a little, Yeah. Even that is the problem with me also. So this thing, so this chunk size is at most n minus 1 by delta minus 1. Is that right? Is this right? This red chunk, that is one chunk, right? And that has this size. Uh, let me just check it once again. Okay. So there is this n minus 1, and then there is this, and we are removing this. Just take it common. Just checking because it's this plus minus thing, right? So minus 1 plus 1 by delta. Right. So that's what it comes out to be. Uh-huh. Okay. Yeah. Yeah, exactly. Right, exactly. So non-chunk, the size of the non-chunk has to be less than delta minus 1, has to be less than equal to this. Is that right? T dash. No, the size of T dash is this, but then the size means the total things that you get in the non-chunk part is less than this, right? So then what did you say next? Sorry. Hmm. Right. Uh, right. So we have to kind of, that is what, so I made a big mistake by while removing this minimum, right? I should have kept that, right? That FV is kind of the minimum. Otherwise, we don't get a contradiction, right? Is that right, Rasuro? You have to kind of use that V was, that's what I, so that's why I'm getting confused because it was there and I kind of removed it for simplicity, but I should not have done it. Right. So that's why I'm getting confused. I'm not getting it. Right. But you made it clear for us. That's good. Yeah. So assume that FV is minimum over all V. Okay. So look, first of all, we are taking, so we are trying to find a vertex V naught for which, so this is how, because when you're using it also, right? We are trying to find the vertex V naught for which FV naught minimizes, right? And then for that vertex, we are claiming that this holds. It may not hold for other vertices, obviously, right? But for the vertex for which FV naught minimizes, okay? Once again, for the vertex V naught for which FV naught minimizes, we can say this. That's what we are trying to prove. Okay, in other words, they're trying to prove there is some vertex V naught for which F V naught is this. That's kind of the best vertex in some sense. How to show that such a V naught exists? Assume that for all V, this is true. Okay, but that itself will not lead to a contradiction. Okay, let us on top of that assume that V is the minimum. V is that vertex for which FV is the minimum. Okay, so V is the vertex for which FV is the minimum possible, and yet FV is more than this. Okay. Okay. So now look at the neighbor of V. Okay, now look at the neighbors of V. So one neighbor is V3, and V3 is the neighbor that belongs to this component T prime, for which this FV is at least this. Okay, so that's why V3 is special. So now we are trying to investigate f of V3, and we'll try to show that it reduces further, and that will be a contradiction. So for V3, to investigate what happens when you remove V3. Okay, so what happens when V3 is removed? That is the question. Okay, so one thing is clear, that when V3 is removed, this part, that is the chunk, that will be one tree. That is clear, right? That will be one tree. And its size is at most n minus 1 by delta, right? So size, so the chunk, that is the chunk tree, its size is at most n minus 1 by delta minus 1. Okay, because iska size is this itself is at least this much. Or you can take equal also for the time. That's the size of the chunk. Now that is one component that you get when you remove V3. The other components that you can get potentially, right? What will be their sizes? I mean, their sizes cannot be more than delta minus 1 by delta times n minus 1, right? Because this total thing itself is, hold on. That is not true, right? Rasuguru, I think we're making another mistake, right? Because this is at least this much. It's not equal. So I'll just remove this thing. Yeah. So far we can say that the size of the chunk is less than equal to n minus 1 by delta. This. Yeah. So what do we do next? Yeah, let's think. Let's not rush it. Let's do it carefully. Okay. Yeah, that is the claim that we want to make, right? So the claim is f of v3 is equal to the size of the chunk. Okay. Okay. That's right. Yeah. So else, so see, if f of v3, if f of v3 is not this chunk, if this is not the biggest component, then the biggest component lies somewhere in here, right? And then its size will automatically be less than, yeah, else f of v3, yeah, this is true regardless, right? Else f of v3 is less than delta, less than equal to delta minus 1. No, I shouldn't, that's where I'm making the mistake all the time, right? Else f of v3 is less than equal to, I just say size of t dash, yeah, that is equal to uh size of fv minus 1, right? Minus 1. Okay, is this clear? Because this is the t dash and one vertex v3 is already getting used, right? So it will be, but the point is it will be less than f of v, and that's a contradiction. It was so easy. Maybe I'm not so fresh today. So f of v3 is f of v less than f of v. That's a contradiction. So f of v3 is the chunk. But then how is that a problem? So claim is proved. Yeah, and that is also something that we have proved. So see, yeah. So so we have this. Right. Is this. So can anybody else say why this is wrong? Why this is not true? I mean, Rasul has seen this. He only told me. But can anybody else see this? Why this is not? Why this is not good? Why this is not good? Well, because we have proved, right? We have proved that for every vertex, any vertex v, f of v has to be bigger than the average, right? But that's why the lower bound was useful. But we showed that f of v is bigger than n minus 1 by delta for any vertex, for any v. So that's the problem. Wait, does everybody see that? Okay, then just take some minutes and just go over it again. I will say it again in a slightly different way now. But let's go through it and just see. So there are no questions. Okay, and let me just say it in a different way. I think this is the way I originally proved it, and then I was kind of getting confused today. Okay, but we still did a proof. This is obviously perfectly correct. Let me just say it in maybe slightly easier way, more, yeah, more straightforward way. Okay, so what is it that we want to show? Okay, we want to show show that there is a vertex for which there is a vertex v naught for which size of the largest component, size of the largest component is at least, no, not at that part we've done, right? Is at most and this is by definition, this is our f v naught. Okay, so we'll try to do it in a more dynamic, little more dynamic way. Okay, if v is a vertex, so first of all, is the statement is fine, right? Okay. If v is a vertex, you can ask a question. You can ask a question right from the start. It's completely okay. We just want to show that there is some vertex for which the size is not too big. Size of the largest component is not too big. So for all components. So if v is a vertex for which fv is bigger than or equal to this. Okay. So just go by, in a, which will look like a non-contradiction proof, but it is contradiction proof in the end, but you'll see. If there is a vertex for which FV is more than this. Okay, so let's say that V is this vertex and it has these neighbors V1, V2, dot, 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 VD. Okay, this, and this is the portion for which FV is attained, and then these are smaller portions. Okay, so this is the portion T prime for which FV is attained. Okay, so if there is a vertex V for which f of V is more than, we're just casually just taking a vertex V. So it's like you start from anywhere, just any vertex, just start from an arbitrary vertex. Okay, I mean, this can actually lead you to an algorithm also to find the vertex. Okay, is that fine? Okay, well, yeah, right. You just start from any vertex and just take its f of V. If f of V is less than this already, then you have nothing to do, so you move on, the problem is over. But if f of V is more than this, then we look at, then there are so many components. Obviously, we look at the component for which the maximum size is attained, right? You look at this component, and the size of this component will be less than f of V. Okay, I just show that. I'm not doing the proof in some sense. You may think I'm not doing the proof, but you will see it will end up in the proof. Okay, so I show that f of this thing, meaning that when def VD is removed from the original graph, okay, I'll just show that it decreases, kind of a monovariant, it decreases. Okay, yeah, decreases, so that the neighbor which has the largest component attached to it, it leads to a decrease in f, in the f function. Now it is something that you can now do on your own, but let's do it. So just try to calculate FVD, and yes, we have done. So the good thing about this is just we are not trying to prove anything in some sense, we're just trying to investigate. Just investigate f of VD. Yeah. So what are the components of f of VD? So now focus on finding f of VD, finding or investigating f of VD. Investigating f of VD. Okay, so what are the trees? Okay, obviously there is one big tree here, and there will be some, now it will have some neighbors. The neighbor that goes outside that portion is clear. Yeah, it may have some other chunks inside. Okay, so V has this chunk which is pretty big, and this chunk is pretty small. It is too small to be a chunk basically, but that is just for intuition. We'll just do the proof. Okay, so if I just call this T1, yeah, then I know that this T1, the size of T1, then this is just calculation. The size of T1 is 2 less. So T1 cannot be the maximum size tree that we have already shown, right? And because T1 cannot be the max component, because we have shown that the max component is at least this much, because this is the average, and minus 1 by delta is the average. We have shown that result, right? F of V, yeah. So f of, basically I'm saying that f of this cannot be T1 because it's more than n minus 1 by delta. Yeah, you can keep this. Okay, so we can take T2, T3, and now it's done, right? Let's say till T5, whatever, T5. Okay, so f of VD is equal to, let's say, some T4, something in this. But the things in this, their size is obviously less than T prime, right? Obviously less than T prime, it's inside it. that is equal to FV. I mean, I've just said the same thing again, but I don't know. Maybe this one is more smooth. You see the point? F of VD is inside this chunk, so it's smaller. So you see the decreases because that this kind of says something very fundamental about the nature of the trees, right? Given this delta, right? That if this if some vertex, the largest chunk is big, then its neighbor's largest chunk will be inside that, and it will be small because the largest chunk cannot be too small. That's kind of the what this is saying. So you see this decreases. This is decreasing, right? Strictly. And so we have done this. So does this finish the proof? Yes, right? Because if you have seen that there is a vertex for which it is bigger than this, then there is another vertex for which it is one less. And if f of VD is still bigger, if it is still bigger than this, then again you can decrease and you can keep doing it till it becomes less than this, and then you'll find the vertex for which the largest component is less than what we wanted to prove. So now please ask questions. I will send some problems, maybe just after the class, you can try. This took some time, but I think we'll just learn some good proof techniques here, reasoning about trees and such. It is not unique. No, it's not unique. I didn't say it's unique. There can be many vertices like this. Right. Yeah. I'm not claiming it's unique. There can be many vertices. Remember, this is the worst case. So even in the worst case, even in the worst case, you can find a vertex for which the largest component has this bound. For good trees, though, you may divide it into half or something, right? You don't know, right? It may be very good, much better than this. But even for the worst kind of trees, this will work. Okay, so let this sink in. Think about this. Okay, we will just do some problems on this. Means you'll try some problems and then we'll discuss this. And there is some legit, like you'll see some good problems. I mean, it will be a mixture of what we did earlier, so spanning trees and such, but some problems which have nothing to do with trees on the face of it. You'll see. Any more questions? Just take your time. Question. Okay, so I'll obviously upload this. If you need to see, you can just see it again, but better you just think now and see if you have any questions. Okay. Okay, try to write the proof, try to write the main ideas of the proof. Okay, I mean, it's not like I'm trying to make you learn the proof, but just the techniques that are involved, just the nature. Try to learn something about the nature of this thing from this theorem, nature of